Good morning, ladies and gentlemen. Dr. John Belkwitz here from Intelligent Concrete. Excited for an amazing day. I'm still here in Chicago working with a concrete precaster to make their concrete stronger and last longer using new and emerging technologies. And that's what I'll be talking about today. We've got a bunch of questions here that I've got to answer. A lot of them dealing with hydrogels, concrete weathering, pollution, concrete pumping systems, colloidal silica, so on and so on and so on. So I'm pretty excited to get into this. It's about 4:30 in the morning here in Chicago, so I'm not as loud and proud as I normally am just because I don't want to be rude and wake anybody else up in the hotel with my yelling, hooting, and hollering. But let's get on to it. So Q&A day. All right, so ding! How does colloidal silica impact the ITZ of reactive aggregate to mitigate ASR? Okay, so if you don't know a lot about ASR, we've got a bunch of videos on them, and I'm not going to waste your time going into that. I'll let you go ahead and watch those videos. I'll have Haley put some links in the description area below. But basically what we see with this reactivity of the silica-based aggregate and the alkalis in solution is the first thing that we need to have is that reactive aggregate. And as long as we have that reactive aggregate, we're going to, and those soluble alkalis with moisture, we're going to see that alkali silica gel start to thrive and survive. Why we normally see it happen at the aggregate is a number of reasons, and if you take out or if you put off to the side the reactive aggregate, I mean, that's an obvious. The second thing is a porous network at the interfacial zone. And this is something caused by the wall effect, which was talked about by A.M. Neville in his book Concrete. And I believe the newest edition has been out for a couple of years now. I think it's like edition 14 or 13 or something to that effect. But it's like page 316, and it goes into great detail about the wall effect. And the concept is the closer you get to a wall or an aggregate in this situation, the more surface area or asperities there are at that surface that need to be coated with cement or a hydrated cementitious matrix. Now the harsh reality is because there's such a high surface area or these high amount of asperities, these little mountains on the surface, there's just not enough paste to cover up or contain that interfacial zone as compared to further distance away into the body of the hydrated cement matrix or the concrete body. Now, because there's all this open porous network, or this matrix, if you will, there's a lot of room for not only moisture migration, but also alkaline migration. And because of that, we start getting this dissolution of our reactive aggregate in combination with the alkalis to create this immature then mature gel. So how does colloidal silica help that, or stop that, or mitigate that, I think is a better way of saying it. And I think you can break it up into three ways. The first way is using the colloidal silica, what we do see is accelerated cement dissolution. So we are creating more cement paste and a higher degree of that cement paste using up our pore solution. So again, where we see that wall effect, there isn't a lot of paste in that area against that wall. Now we're increasing the total paste content. So we are creating more paste at that interfacial zone, closing up that porous matrix, not really giving the room for a lot of pore water and alkalis to migrate into that open area. The second thing is actually locking up that moisture. What the colloidal silica does is it consumes calcium hydroxide to create more of that backbone of concrete strength, the calcium silicate hydrate. But that phase development cannot happen without H2O. After all, we're still dealing with calcium hydroxide in solution as it's consumed by the silica to create more of that calcium silicate hydrate. So we're locking up that moisture that would transfer those soluble alkalis from the body of the hydrated cement matrix to that interfacial zone to create or to cause that ASR, that alkali silica reaction. And the third and final piece of this is those actual alkalis themselves. And the higher the degree of cementitious hydration, whether that's pozzolanic reaction or accelerated cement dissolution, the more we can chemically bind those alkalis so that if there is migration or moisture movement, that moisture can't carry those free alkalis throughout the hydrated cement matrix to the interfacial zone. Ultimately, we're anchoring those soluble alkalis that would contribute to the ASR, and making sure ultimately that concrete is stronger and lasts longer. So hopefully you got something out of this today. Don't forget to like and subscribe. Let us know if you got any concrete questions, concrete concerns. Go concrete, beat asphalt.